There you go. So what the question that come up now is we first we're talking about the dissections, and so let's just talk about that. So one question that comes up is, do we need to refrigerate the specimens? And the answer to that is no, you don't. And apparently there's a yellow paper inside the back, the kit, that explains how to store them. But they are preserved in fluid, so they should be okay. But do not keep them in a hot car. Do not refrigerate. Oh, look at that. Do not refrigerate or freeze.
Oh,
Leave
shit.
fluid. I'm sure it's going to be okay.
Okay.
Well, it doesn't. It just says there's not like a need to. I don't think it matters, right?
Yeah, well, it says do not refrigerate or freeze. So I think that you don't want it to be too cold. So I think
Maybe just take it out.
Yeah.
huh?
She's gonna go take hers out of the fridge.
There you go. Leave fluid in the bag. Do not drain, and keep out of reach of children and pets. All right, don't give it to me then. Leave it away from me.
Yeah. So there's the brain. I don't know. If
Oh, cool. Excellent. Yeah, I think, we're trying to get, I didn't realize that they're doing that. And then when I found out, I thought it was really cool because feeling some of those tissues, how the brain feels mushy and the heart muscle, it's kind of nice to be able to, get that texture and that tactile sensation with it. And so, did you guys look at the modules yet for the dissections?
I have not had a chance to look at
So
them.
let me go through it briefly then.
Okay.
The eyeball is so disgusting.
It
I
is.
know. I saw it right now. So looking at me.
Well, in class we do a rat, and I can't touch rats, so it's always really funny because I'm the squirmish one, and I'm the teacher. So.
Oh no, not a rat.
No, I don't. That's what they have. I know. So I thought, I don't want to send rats home.
Yeah.
To you guys, I think organs we can handle that, but full. When we have tables of 4 or 5 people, you always have 1 or 2 that are really into it, and a couple others stand back a little. But I think organs are okay. I think.
Yeah, I'm a TA in an anatomy class for my first period, and it's so funny because they just finished dissecting piglets, like little pigs.
Mm-hmm.
And it's so funny when you like see the group, there's always like one person, they're like, let me cut it, and everybody else is like, I don't want to touch it, don't give it to me.
I know. So
funny.
So I think organs we can handle a little bit easier. So when you can see my canvas, right?
Yes.
So when you go in the modules, I put, and for this semester, you guys are lucky from that perspective. You can totally secure your A by doing these things because they're extra credit, because they're added in. So I have to, be a little sensitive to that. And so, but I do believe it's a really good exercise because, again, you can feel the tissue texture differences, and that tactile experience really helps. And so under heart, I put the sheep heart dissection. And when you open that, you have a little read up, and then there's a little video that works through it. And basically what you do is you copy the video. And then I want you to identify these structures when you cut that heart open, and you make a little video with a tripod or with somebody else can do it, and show those structures on the video, and then you upload it onto Canvas. I mean, yeah, it is Canvas, not Moodle anymore.
And it's those 4 structures.
Huh?
It's just the 4 internal structures and
the for the showing, again, I really believe it's very important to feel the tissue. So when you work on it, what I want you to cut it and go according to what the video shows, But then when I want you to make the video, I want you to identify the 4 chambers, the AV valves, the atrioventricular valves, those little tendons, the chordae tendineae, and then the interventricular septum. And on the outside, we have auricles, we have the top and the bottom, the apex and the base, pulmonary trunk, aorta, and supravena cava. Those are a little bit harder to identify, so there you can get a probe and push through from the inside out and sort of figure out which one is where. And then you make a little video with showing me those structures, and then here are instructions how to upload that video. I think when you upload the video, let me just do that real quick. When you upload the video, if I can, yeah, you go here. No, here. This one to video and music. And there you can upload a record medium, or you can record a medium. And so you can upload by dragging a file here. That's the video file. So if you use your app on a phone, that's probably the easiest, because you can make a little video with the phone and then you can upload it on the app over the phone like that. Yeah. Don't put it as an attachment if you can help it. But don't put it as put it through this icon right here, the media upload or record. And maybe on the phone you can directly record it onto Canvas. I don't actually know how that is, because it says here record media. You could probably record that as well. Right. I haven't had that in my classes that I take. And then after you upload it, then you can see other people's uploads too. So if you watch a couple and you go like, oh, darn it, I messed up here and here, you just make another video and upload it again, and then I'll take that one.
Okay.
You know, so that way, and then, you know, and after you've done it, text me or talk to me about how the process goes and how smooth and difficult that is. But so we have one for the heart. So that's under the heart module. And then we have one for, come on. Oh, there we go. We have one for the brain right in here under the brain module, the sheep brain. And again, you have a video, and then here are the structures I want you to show me on that brain. And then, hi, Yanka. And then we have brain, and what else do we have? The eye.
The eye.
Is under the special senses, I think, here. So let me close down the heart. Yeah, there's the cow eye dissection under the heart, under the special senses. And then the kidney is under the urinary system, right here. So we have four dissections we're doing. Is there any question to that, or is that pretty clear?
No, it's pretty clear. I had I was looking on the app on Canvas, and so when it says when you can like submit it, hold on, get back to it. It goes to like this screen right here, and then if you press like the little like plus sign,
and there you can then take a video, right?
Yeah, it'll let you record. Is that how you want us to?
Yeah, let's do that. That's the easiest, I think.
Yeah, and then you
can do that, or yeah, because I take a picture too when I upload stuff in my class that I'm taking. So yeah, if you could do that, that would be the best. And then yeah, you can just make a video. And so it's like when you upload the homework on the picture, it's just a video instead of the homework. And if you don't have that function or that app, well, try to get the app, because it's actually a really cool way to do work.
It is super convenient.
Yeah, totally. I mean, I take my tests on there even, because then I can use the computer for, you know, if it's an open book test, I can use the computer for referencing things versus the phone. It's better. It's easier that way for me. Yeah. But yeah, and if not, if you have to go through the computer, you somehow figure out how to download the video onto the computer and then upload it from there. But, you know, that's a little bit more cumbersome. Good. So if there's any questions with that, you know, just speak up through the Zoom call or shoot me a text. with questions, and I'll answer them. Since this is the first go around, I'm expecting some questions, so don't feel hesitant to just reach out, even if it feels like something dumb, like, you know, I might have forgotten to turn something on or off. So make sure to talk to me. So with that, I want to move on. I think we can leave test 2 behind, the muscles and the bones. If you have any questions in terms of the test, I've graded them all that were in. If you have any questions, please text me, reach out. I'm happy to communicate with you and individually talk about questions or about responses that don't make sense to you. So we can, you know, I can talk to you individually about that over the phone or over text, however we need to do it. What I want to do today is I want to get us through booklet number 4. So today we do a whole booklet. So we're going to go from the heart through the immune system, blood, immune system, and then blood vessels, and then endocrine system, and we finish up with the integumentary system. So that's quite a bit of information, right? Huh?
Sorry, I have a question for the homework.
Yes, talk.
Okay, so hold on.
Yeah, I could see.
Is this thing, not that thing, this thing, is that called the medulla?
Yes, you got the pyramids in the front.
Okay. All right, that's all I had. Thank you.
Got it?
Yeah.
So that was part of the brain. So that's perfect. So as we get to these homeworks, we can go right to the anatomy. Oh, actually, let me get out of this share because we don't need to do that right now. We can go right into this part again, the anatomy labeling exercises. And there we are now on term list number 2. So we finished term list number 1 with the muscles and the bones, and now we're just working our way through the rest of the material. We're starting with the heart, then we have some blood, and then we go to the brain, and after the nervous system, including the eye, the ear, we have digestive, lungs, kidney, and reproductive system. So just work your way through it, label all the terms on the term list. You don't have to label other terms. You can always do that if you want, but I'm concerned that you know the anatomy terms on the term list, because for the final exam, the last exam, it's not accumulative, it's all just sectional. For that exam, again, we have, like the second exam, we have terms that I want you to identify, and they come all from the term list number 2. We don't gonna start doing a quiz today, but after next week, when we do the brain, we start doing quizzes again on the Zoom call to get us ready for that part of the test. While I'm at it, there at some point, I think you guys have been doing some of the health kit stuff, right? You've been doing the salt intake. How is that? And did you do the injury thing? All the how many squats can I do?
Mm-hmm.
Yes.
Yes, those are actually the injury prevention thing is how they is orthopedic. So that's really higher end. I want you to keep that handy, because that's something that if you know, go back after a season or so, or haven't worked out in a while, those are good things to kind of do once in a while to check, hey, am I strong in these side muscles or so forth. And they do those tests at the clinic in Zurich, where they do the Olympic athletes and the ski athletes. There's a lot of skiers in Switzerland, of course. So that one is an interesting one. Did you guys find some help in that one, or also the posture or the ergonomic one?
Yeah, especially the posture one.
Good. You got some tips out of those?
Mm-hmm. I have horrible posture.
Me too.
And my back hurts all the time because of it.
The way I'm sitting,
because I'm getting old.
Oh yeah, thanks. I want ancient. I know posture is a hard one. I mean, that's, you know.
I get like tired trying to
sit up. I know, it's like, oh, that's why you got to you get a foam roller and lay over it or something to counterbalance it, you know, or a gym ball if you have room for it.
Yeah,
something like that. No, I think it's good to once in a while look at that, especially also since we're working at home so much, and it's like, oh, the couch or the bed, it's really nice to sit in after 8 hours. It's like, oh my God, everything hurts now.
That's
So
me
that's,
right now. I normally sit at my desk right there, but today I was just because I have like I go to high school, then I have volleyball practice right after, then I rush home and get on my Zooms. So then I'm like, today
no,
I'll
sometimes you just need to not worry about none of that.
yeah.
Yep, absolutely. I think so. No, I think that's very important. Well, and you know, I put that exercise in there too, is the posture where you hold your chin and then you bring your head back to kind of take the pressure off for these. I don't know if you've been doing.
Yes.
Sometimes I have to, you know, I do these so I remind myself a few times a year as well, because it's really easy to forget, you know, all
Yeah.
that stuff. But you know, anyway. So I hope you're enjoying them more or less, and they give you some help. So yeah, good. Yeah,
Yeah.
yeah, good. Um, then let's go now to how, so the anatomy terms and those exercises is part of how the test 3 is going to be. So it's a little bit like the second test for the term list. But then also we have some other things that we want to talk about that aren't just pointing at structures. And those things are done in a test format that's like the quiz, regular, like the test number 1, multiple choice and true false. And as you probably noted yourself or saw yourself, we got a heck of a lot of material to go through until we do the final. We have 3 booklets, and so what I've done is, instead of making more than one more test, because I don't usually want to lose time in the classroom. Maybe now I could structure it a little bit different since it's online, but I don't like to lose too much time with doing too many tests. And so what I've done is, for test number 3, I've done a really thorough test review. And so you can see my canvas, right?
Yes.
Good. When you go into the test thing here, and I should take this out for now. We don't need, no, I leave it in. You go to test review, and in test review, you see you have a test review, which we're going to look at in a minute. You have term list again. That's the same term list that you already have, just in case you need it again. And then you got these videos again where I look at all this, or point at all these different structures. So what I want you to do is, I want you to go on your device or somewhere on your app or wherever, and you're accessing all this stuff from, and go to that test review. And what you will find is, you will find a 4-page review that has the chapter title. I should say chapter number so and so, but I haven't reviewed. I haven't updated this in a hot minute. There's always so much to update. But look at all these bullet points. So today we're going to talk about the heart, the blood vessels, the blood, the immune system, endocrine system, and the skin. So we're going to go through 1.5 pages of things that could be on test number 3 from the booklets. So that's from within the booklets. And so I'm not looking at covering on the test, covering all the chapters in full. I'm kind of picking the things, or some things that I find are important, and asking you questions on those. And all of those data points are listed on the test review. So as we get through the heart, you can see in your booklet number 4, I believe, yeah, number 4, you have on page 12, you have an EKG or an ECG, an electrocardiogram graph. And you can see that line, and on the right side, it indicates what each of the waves are. And here you have a list saying what they are. And so let me actually go to that real quick right now. PowerPoint. You can see my PowerPoint, right? Right?
Yes. Yeah.
I know I get anxious, but then I need a little. Can you see it? All right, here's the EKG. That's page 12 in your booklet. And you can see when you have that tracing, you probably all see that tracing sometimes even on an ambulance side of the car. There is these bumps. The first bump is the P wave. And the P wave, well, actually, what does an EKG measure? An EKG measures the electrical impulse that travels through a heart muscle. And what's interesting about the heart muscle is that all the heart cells are connected with one another, letting ions go through. And what that does is you can have a nerve impulse spread through the whole heart in one swoop, and all those muscles that are muscle cells that are different muscle cells, but they all contract as one. And that's why the heart is not contracting a little bit here, a little bit there, and a little bit everywhere. It contracts as a whole unit. And they call that the functional syncytium. And that impulse that travels through the heart is actually generated within the heart itself and starts here on top by the atria and spreads through the whole heart, all the heart walls, the atrium and then the ventricle. And what's interesting about this is, well, that the sinoatrial node initiates that impulse about 60 to 70 times a minute, and it actually happens to be an ion leakage that makes that happen, which is kind of interesting. So it's a leaking cells that make your heart pump in some aspects, if you think about it. And then that spreads through the top part of the heart or the base, and that is where the atria are. And when those contract, all the blood that is in the atria, which are the receiving chambers, which get the blood from the body as well from the lungs, then that blood gets squeezed down into the ventricles. And at that point, the ventricles will contract. So they will contract slightly later than the atria. And the impulse gets actually picked up here by the second node, which is known as the Atrioventricular Node, right in here. Should be right here, actually, the green one. Oh, it is right here. This is the bundle of his there. There's just no arrow. And so when the impulse then gets picked up by the AV node, it intensifies and gets spread through the ventricular walls. And then those ventricles contract in unison again, slightly behind the atria, and push that blood forward through. And let's look at that part of the whole thing. The blood goes from the atria into the ventricles, and then it gets pushed through valves into the pulmonary trunk, which goes to the lungs, or into the aorta, which brings the blood then to the body. And so when we look at this EKG tracing or ECG tracing, we look at that electrical impulse, and we can get a whole bunch of diagnostic information out of that, how the heart works when we look at that electricity. The other one we think we do is we listen to the heart and see how, well, as a fundamental sort of thing, and listen to the valve closers. We'll talk about that in a minute. And so this first bump here, this P wave, is when that atria contracts, or when that electricity goes across the atria. And excitation in neurology terminology can also be as a term called depolarization. And when we get to the nerves, we understand that much more what depolarization means. But when you look at a nerve, the inside and the outside of a nerve is slightly different in how many charged molecules it carries, or what the charge is. And so the charge is usually slightly negative on the inside of a cell, of a nerve cell, and slightly positive on the outside. And when we have ions, remember from chemistry, we have ions. These are charged molecules, and we can get ions going from one side of that cell membrane to the other side, into the cell or out of the cell, and we can shift that how much polarity is between the inside and the outside, how much difference polarity is, how much difference is the charge between the outside and the inside. So it's a slight amount of electricity. We'll talk much more about it when we talk about the nerves next week. But the depolarization is when we excite, when we send a nerve impulse through through the body, and so the P wave is when that atrial excites, or when that atrial, that SA node depolarizes. And then the QRS complex is when that whole thing, that impulse spreads over the ventricles. So that's then known as ventricular depolarization. And so these terms you'll learn much more when you get to the neurology next week, or later this week, I guess. And then the last bump we have here is the T wave. And the T wave is when the ventricles, the excitation finishes. And so the depolarization is finished. And what happens there, when you look at how a nerve impulse spreads, it's with electricity. And the electricity charge changes between the outside and the inside of a cell. But when you look at who changes that electricity, it is ions, and ions carry a charge on them. And so in nerves specifically, you have sodium ions and potassium ions, and they're both positively charged ions. And so when you have a nerve impulse, you end up having sodium ions bring positive energy, positive electricity, a positive charge to the inside of the nerve, and that's depolarization. And then you want to stop the nerve impulse, you bring the charge of another ion, the potassium ion, which is also positive, and bring that to the outside of the cell. And then but what happens is you have the chemicals scrambled. And so you have to reshuffle the chemicals that you can send an X nerve impulse again. And that process is known as repolarization. And that is that indication of the T wave, what we see there. Anywho, does that make a little bit of sense? Or is that like way, oh my Lord?
It makes sense.
Makes some sense? Okay.
Yeah.
Good. Yeah, because so that's the first bullet. So what I want you to know is, and now let me get back to the screen. I think we had it right here. That's that bullet number one. What are the waves indicating? So all the other explanation is for you to understand it. What you need to know for the test is what these are. But I want you to understand it. Otherwise, it's kind of a mute exercise. But when you study and when you go through the chapters, you listen to the video and you look through the booklets and you do the quizzes and you do the labelings, but then you make sure that you really memorize these points that are here for the tests, or make flashcards. I think I would make flashcards out of that. I mean, it's already, well, it's a pretty fast semester, but flashcards are really cool to study things because you write down something that takes a little bit of time. It seems a little odious, but once you've done that, all you do is you remember what you've written down and what you understand. And then the cards, you have a system that you don't go through the stuff all the time. You just end up going through things you don't remember as easily, and you study on those and focus on those. And so as I went through college with chiropractic school, which is quite intense, that really helped me with my studies, so I wouldn't study excessively. But so that's why I put that little card together that I sent you in the beginning of the semester there. Anyway, so the next thing I want you to know is the difference between systole and diastole. And systole is when a heart contracts, and diastole is when the heart relaxes. So when the heart squeezes, that's systole. When a heart muscle doesn't contract and the heart can fill up with blood, that's diastole. You know that from the blood pressure. If you take a blood pressure, you have a higher number and a lower number. The higher number is the blood pressure, measures the force that the blood pushes against the arteries, the walls of the vessels. And so when the heart contracts, that force is greater than when the heart is relaxed. And so the first reading on the blood pressure, the higher number, is the systolic blood pressure when it contracts. And the second number is the diastolic blood pressure, which is when it relaxes. So then after that, we're going to go to the sounds of the heart. We have two sounds of the heart. We have lub and we have dub. And when you look at what the sounds are, they are when the valves we have. When we look at the heart, we have these. Let me show you a different picture here again. Let me show you this picture. We have the two types of valves. We have the AV valve, the atrioventricular valves, which actually what they do is they guard the backflow of blood from the ventricle to the atria. So they close that door, so to speak, when the heart down here contracts. And if you visualize that, when a muscle contracts, it shrinks, it gets smaller, it pulls together. And that makes sense because you got this blood, this volume in here, this chamber, and we want to squeeze that blood out of the heart. And so when we make the chamber smaller forcefully, that will squeeze the blood somewhere. And in order for the blood to get squeezed the direction we want it to, we got to make sure it doesn't go back from the ventricle to the atria. And so we have these flaps here, these cusps. Cusps means flaps, that when the heart muscle contracts, they come closer together because the muscles, the chordae tendineae and the flaps get pulled upward a little bit as the muscle contracts, and everything gets closer to one another. And then they cover the hole between the atria and the ventricle. And so no blood will go back from the ventricles to the atria, unless you have a heart murmur, which is, the murmur is the sound, the shush sound. And it could be that you have an insufficient working valve, and you have a little bit of leakage going on. So that would be a murmur. Then so that's one set of valves. We have one here and one here. They both guard between the atria and the ventricle. And then we got a set of valves that guard between the ventricle and the great vessels that the heart pumps the blood into, or the ventricle pumps the blood into. And those are the aorta and the pulmonary trunk, sorry. And the valves here that are the guarding valves are the semilunar valves. And so we have one called the pulmonary, that's right by the pulmonary trunk, which is, even though it's purple here, and the purple means it's not vascularized blood, but it also kind of indicates to us that even this is a bluish vessel, which indicates deoxygenation of the blood. It is also an artery. See here, it's an artery. And because arteries are actually vessels, the definition of arteries is that they're vessels that bring the blood away from the ventricles. They lead away from the ventricles. So these are high pressured vessels. And so if you think about the pressure, it's like water pressure. Hydrostatic pressure is when forcefully the heart pumps the blood into the arteries here. That's a very strong force of, water stuff pushing through a vessel. And so these vessel walls need to be really strong and be able to withstand that. And so that's why they are termed arteries, because the veins, which are the vessels that bring the blood back to the heart, mainly you see them here, the vena cava, and then in the back here you see the pulmonary veins. Those are low pressure vessels, because they don't have a heart that pumps the blood into them. It's more like molecules that stay behind the heart after the blood gets squeezed to the tissues in the muscles or somewhere. They suction the blood back into the vessels, which is kind of like when you put salt on a piece of tomato and all of a sudden the salt crystal is a water droplet. That's the pulling of the salt crystal, pulling the water out of the tomato. And you can think of the same in a blood. As the blood goes through the arteries and gets then squeezed into the tissues, some molecules stay behind and they act like the salt on the tomato. They suck the blood back into the vessels. There's no hard pumping in those muscles and the other tissues. And so that blood then gets brought back to the heart via different mechanisms. One of them is, for example, they have valves. So they have some valves that are looking like these valves, actually. They don't let the blood fall back down as it gets brought back to the heart. You also have the vessels, the veins go through muscles. And so when muscles contract, they also pump the blood towards the heart. But it's not a high pressure event. It's very like just guide the blood back to the heart event. And so the veins, the walls of the veins are very different. They don't have to be so thick. They don't have to withstand that hard hydrostatic pressure, that strong pressure. Anyway, that was a lot of talking just for the valves. But the valves close. And so these hard sounds are made when the valves close. And so the first valve that will close is this valve. So the AV valve will close at the beginning of when the heart contracts, that the ventricles contract. And then the blood goes, well, when we look at the cardiac cycle, the blood goes from the atria into the ventricles and then from the ventricles into the great vessels. So just looking at the right side here, it's easier. The left side is right over here. And so as the blood goes into the ventricle, then the atria contracts slightly and push it downward. That's when the SA node fires. And then right briefly after that, this muscle, the ventricle starts contracting. And as it closes, these valves close. And so that's the AV valves close first. And then these valves here open because the blood, the hydrostatic pressure pushes them open and the blood goes into the pulmonary trunk or the aorta. And when this heart muscle stops contracting, there's a little bit of blood left and that will fall back down and will close these semilunar valves. And so they're sitting here, which then makes it so it's a little hard to push that open, but you want to have this little moment where the pressure increases and then forcefully it opens the valves, because that's the way we get all this blood smooshed around through the aorta and then through the body. So it's a pretty interesting event. It's a pretty powerful situation. And so when these valves close at the end of the ventricles contracting, then that's the second heart sound. And so we look at them as sounds. The first, the lub, is when the AV valves close, and the dub is when the semilunar valves close. Good. You guys gotten that?
Yes.
Good. Yeah, it gives me a moment to not talk. My jaw is already hurting. So then this slide is about where you can find hard sounds, where you can specifically put your stethoscope and find which valve is closing. So that's where the sound is projected. So that's pretty cool. And then here we talk about the murmur a little bit, but what I want to point out to you is this Kyriac Cycle slide, because this is actually a pretty cool slide showing everything. It shows the pressure in the, that happens in the atria and the ventricles as we contract. We can see, so this is the atrial systole, here's the left atrium, this is the aorta here, the pressure, and then that's the ventricle. So this is pretty interesting. And then the volume, you can see how it all of a sudden it drops down and then it fills back up. That's and that's when the ventricles fill, and then that's when the atria contracts a little and fills a little bit more. And so here you can see the valves, the AV valves, and then the semilunars, they say here aortic and pulmonary valves, and when they're open and when they're closed. And here you see the dynamic of what happens with the blood, where it travels and where it is in the traveling. So it's kind of an interesting overview slide. So I know I always have to slow myself down, and that's why I'm reading some of these things, because I glance over this in my own classes, and it's like, no, wait a minute. If I slow it down, it's not a mystery. I understand what it is much more. So anyway, this is that's why I put this one in as sort of an overview slide. for the cardiac cycle. But what we have there as a last bullet in the heart is the definition of cardiac output. And cardiac output is how much blood gets pumped in 1 minute. And it's basically a function of how many times we beat per minute, how many times that the heart contracts. And then the second thing is how much blood gets squished through each time we contract. And so then we multiply those two. So it's heart rate and times stroke volume. That's what the definition is. And so it's a volume of blood pumped in 1 minute. What's interesting is you can really exert that and go up to, from about 5 liters here up to 25 liters. You can 5 times that thing if you have to. So that's kind of cool. If you need to run away from the lion, you can run real fast. Good. With that, let's talk about the blood vessels. We already talked about a bunch of those things here. We say arteries lead away from the heart, veins leads to the heart. And this is on the test review. It's just the blood vessels, the second bullet here, and then we get to blood. So I would urge you guys to print that out and use that, as your kind of guide also then when you take the test, because it's an open book test. It's not a closed book test. So you can use all the help you can get. All right, let's go back to this stuff. So arteries lead away from the heart, veins leads to the heart. And capillaries are in between. Capillaries form areas where gases such as oxygen, carbon dioxide, or substances such as glucose and waste get exchanged. So that's what I want you to know that about capillaries generally. And then we talk briefly about lymphatic vessels. Lymphatic vessels are interesting because they pick up excess fluid and bring it back to the venous supply here right by the heart. They also pick up fats from the digestive system and bring it back to the heart, and then goes then to the liver for processing after that. We'll talk about that when we get to the digestive system. But the lymphatic vessels run parallel to veins and help them pick up fluid that is pushed out out of the capillaries and has not returned back to the veins. So that's the main thing I want you to understand what lymphatic vessels do. Okay, they are they're also filtering the blood. That's another thing that they're doing, because they have these lymph nodes that the fluid has to go through, and that becomes an immune function. So we'll talk about that when we get to the immune system, which is in a few minutes today. We have to do that today. But that's unfortunately also how we can, well, first of all, the lymph nodes is where we have a lot of white blood cells that help detect foreign agents or pathogens, things that make us sick, and they can eliminate that in lymph nodes. But the negative is it's also
I have a question.
Yes.
Where are the capillaries located?
The blood or all of that, they're in the tissues, in your muscle, for example.
Okay.
Yes, if you look at the vessels, the arteries carry the blood from the heart to the tissues. Let's say that's a muscle or the heart itself or any tissue in the body, and because everybody needs pretty much be perfused, maybe not cartilage, but you still need to bring the nutrients to the cartilage somehow. And that's the capillaries where we have that exchange of gases, that exchange of glucose or other nutrients, and then also waste. And then from there, all of that material gets brought back to the heart via the veins. And so the veins and the arteries are not vessels where we have an exchange of these fluids. That's in the capillaries. So the veins and the arteries bring the blood to the tissues, and the veins bring it back to the heart for pumping.
So do the lymphatic vessels, they run next to the veins and they also carry stuff to the heart?
Yes. And so when, I talked before about how those molecules like the salt on the tomato kind of thing, where some substances stay behind in the blood, they're too big, they can't squeeze through it. And then they help bring the fluid back into the venous system. But some of it stays behind because it's not as efficient. It's not 100% efficient. It's pretty good, but not 100% efficient. And so that's what then the lymphatic vessels pick up that excessive fluid. Does that make sense?
Yeah, that makes sense.
And you see that, like, if somebody they have like, let's say they have cancer and they have to take the lymph nodes under the axilla out, under the armpit, they have to wear a sleeve so their arm is not getting puffy and filled with fluid and swollen, because the lymphatic system is not working as efficiently in that area then. So that's why that is. So that's where you can sort of see what happens when the lymphatics don't do that work, or not as well. All right. And now I forgot what I was saying about the lymphs. I think we said most of the points, and we'll talk about the immune system in a little bit. Then I like this picture where you can see all the perfusion with arteries in the body. You see how much the head gets. Of course, the lungs, and then liver and digestive. So that's pretty neat. And here you see the different namings that I kind of just put together, because we're not really learning too many of these names in here because it's a fast moving course. But what's interesting, the aorta I want you to know, of course. But what's interesting, you have like hepatic means liver. And so that goes to the liver. So you have these different names that indicate the organ that they go to. Renal means kidney. And so you have iliac is where the hip bone is. So you have a lot of these names that reflect, that are telling you what's going on. I mean, you might have to learn, hepatic means liver, but that's good to know that anyway. And by the time we go to the liver, you know that word. Pulmonary is lungs, for example. And then the veins have similar names. You just say veins versus artery. Or when you go into the arm and to the leg, you see a lot of them where are they? Subclavian is under the clavicle. Sub means below. Axilla is in the armpit. Brachial is by the arm. By now we know what brachium means with all those muscles. And then look, radial ulnar, that's by the bones where they run. And so a lot of these, you can sort of, once you know the bones and the areas, you can kind of make out what their name means. Femoral is by femur. Iliac is by the hip bone, ilium. Tibial, we have a peroneal, that's fibular, but the old name is peroneal. And then the venous system is very similar too, except in the venous system, we have deep veins and we have superficial veins. So some run deep through the muscles because the muscles help, the muscle contraction helps the blood go back to the heart, and some run superficially. And so you have, like in the arm, you have a basilic vein. That's a different name. That's a superficial name. You have a cephalic vein. That's a superficial name. So you have the ones that are named like the arteries, axillary, brachial, radial ulnar. Those are deep veins. And then down in here, you have superficial. The antebrachial, the cubital is also superficial. Anyhow, I cut off the hepatic. I should cover that up. And then in the leg, it's very similar. You have deep and superficials, and the superficials are the saphenous is a superficial vein right in here. Yeah, I think that's the main one here. And then when we get to the head, what's interesting about the head, a perfusion with blood, is that we get an internal carotid bringing the blood to the head, the brain, front cortex, part in the front and part in the side. And then we have a vertebral artery that brings the blood to the back side of the brain and the cerebellum. And so those are these two arteries that carry blood up into the brain. We have other ones. The external carotid feeds the face and all of that, but from terms of the brain. And then those two circuits, they are connected with each other. And so that's interesting because if we need a little more blood from the vertebral artery, we can get that fed to the front part of the brain or vice versa. So that's kind of, assuring, we're trying to assure that the brain really gets oxygen, because if the brain don't have oxygen for a while, that's not a good idea. Brain nerve cells die really fast. And that brings me to the last part of this one here on the blood vessels. And we were talking about arterial blood pressure. And I mentioned that before when we talked about systolic and diastolic, contraction versus relaxation. And so when the heart contracts, the pressure waves against these arteries are much greater than when the heart is in systole and it doesn't contract, it's relaxed. And so the blood pressure is the pressure against which the left ventricle must eject blood. This pressure wave can be felt in superficial arteries. So that's what I want you to know about blood pressure. That is the pressure wave. Good. And with that, we're going to go to the blood. So look, we already done this. So now the blood is a little bit more involved here. We have these different blood cells, and then we do the immune system, endocrine, and skin. So I just got to read through those bullets. That way we don't jump back and forth too much. But you can always stop me and ask me what's going on and what would like to highlight a little bit more. Make sure. All right, blood is. Make sure you interrupt me and don't let me just run wild. So blood is connective tissue, and connective tissue has cellular components. That was chapter 4, cellular components, as well as an extracellular matrix. And the cellular component of blood cells are red blood cells, white blood cells, and platelets. The red blood cells help us with carrying the oxygen around and the carbon dioxide. The white blood cells are immune cells, and the platelets help us with coagulation. And coagulation is when you have a cut in your vessel, like you cut your finger and you bleed. Some vessel is cut. Now, how are you going to make sure we don't just lose blood? And how does it stop bleeding? And that's what coagulation is, the process of patching up a broken vessel wall. And that's kind of an intricate process because we got to make something solid in a fluid thing. And so we want to make sure we only make little solids right where the blood vessel is cut, not, have solid things float around in the blood itself, and then they're too big and they clump together and they create a blockage in a small little artery in the brain or somewhere, and that's a clot and that's a stroke. And so we need to be very, very careful how to regulate that process. And so that's the process of coagulation. Good. So those are the cellular components. And then we have the extracellular matrix, ECM, they call that in short. And that's usually a ground substance and a fiber. And in blood, the ground substance is like water, liquid. It's blood plasma. In bone, that's the calcium things. The calcium, that's why bone is hard and blood is liquid. And it's like, is that the same tissue type? But it is because it has all these components. And so for us, that makes it the same tissue type. And it's about the embryonic origin of how these tissues are created and all that kind of stuff. But for us, what's important is we have a cellular component and then the extracellular matrix component, and that is blood plasma, and then we have fiber. And in blood, we have to have fiber, like when you have Metamucil, the fiber that you can put in water and you don't see anything, but you actually drinking fiber if you don't like to eat your apple or the strawberry. But we have to have soluble fiber. So we have to have a fiber that doesn't clump out and clump together and becomes solid. And so we call that the fiber we have there is fibrinogen instead of fibrin, which is the insoluble fiber, which we're going to get to, that we use to patch the blood vessel when we really need that. We have a form that's inactive, and it's called fibrinogen. And when you see that GEN at the end, it's a creation. Genesis is the creation. And so then it's an immature form. It's not quite finished yet. So it's still in the process of being made. And so that when you see that term, you get the same thing with enzymes. Like in the stomach, you have an enzyme that digests protein, and it's known as pepsin. And I'm still thinking that Pepsi Cola's name is from that. But anyway, that pepsin is the active form of an enzyme that digests protein. But you don't want to have that be an active form when you're not eating, because otherwise it starts digesting your stomach wall, because that's protein. And so you have an inactive form of that enzyme. It's known as pepsinogen. So you have that GEN again at the end. So if you see the suffix with GEN, you know it's some immature form of some kind of a thing. And so that's kind of good to know, I think. And so we have then the extracellular matrix is those two things, the plasma and the soluble fibrinogen. And then we go right into the function of blood. And we have a function of blood as what we know about blood is transports oxygen and carbon dioxide. Oxygen from the lungs to the tissues, carbon dioxide back from the tissues to the lungs. We need oxygen, as a reminder, we need oxygen to make energy, to make ATP. So we need oxygen and food for us to be able to make energy, which is sort of the most vital thing we need to survive. So pretty important stuff, this RBC stuff. And then we also talked that we have white blood cells, and that part is the immune system. So we're going to talk about how the immune system works a little bit next chapter. But here we talk about the different cells that make that up. And then we get through the plasma, we get substances transported through the body, like the glucose, like the nutrients, or also like waste or other things like hormones or vitamins and minerals. And then another thing we have happen is we can have heat distribution done by the blood. Liquid holds a lot of, has a high heat capacity, so it can absorb a lot of heat. And then we can, for example, if it's too hot on the inside, we can take that blood and bring it to the surface of the skin. And so we're blushing when that happens, but the heat's radiated off into the universe at that point and away from the body, which is cooling down the body. Or we can also, when it's too cold, we can preserve the heat on the inside of the body, and the blood goes away from the superficial skin, and we get pale and freeze our fingers off. But that's much better than if our heart gets frozen, or if our no pun intended, or if our liver freezes off. That would not work. We could not survive with that. So that's where we can distribute heat around in the body with the blood. And then we talked briefly about that blood coagulation. That's like where you get that cotton. And that's where this is the fibrin. So fibrinogen is all floating around here. And when you have a blood clot, the process makes this fibrin, these fibers here. And then the platelets are these things that we have as cellular fragments. And they clog that thing up and patch it. And the fibrin also traps red blood cell. And then that, at some point it becomes your scab, if it's on a knee or on the surface of the skin. And then after the scab falls off, or the blood vessel is so to speak, the scab falls off from the blood vessel, all of that gets dissolved because it's healed. And then this fiber needs to be dissolved so it doesn't get lodged off into this bloodstream and then gets, clog something because it's too big for the small little vessel's diameter. So that's why that is a very delicate process, but that's a function of blood also. Let's see what else we have. I think that's about good for the functions. Transport. Yep. So then we can go right into the white blood cells. The rest here is about the red blood cells, this part. And then we go into the white blood cells. And so that's immune function. And so I want you to be able, in the practical part of the test, I want you to be able to identify them like how they look. So you want to kind of know the fact that there is some that have granules, and depending on how the color of the granules stains, they call them different things. So Well, they are different, but they also call them I think according to the granules, because the ones that have the granules look similar to the background, they call them neutrophils, like neutral. And then the ones where it's more reddish, they call them eosinophil. And I'm thinking of neon light or something. And then the ones that are bluish, darkerish, they call them basophils. And I feel like, I don't know, that seems a little more bluish to me, the basic versus red hot or neon light. So that's how I identify them. I don't go with identifying wise with these. I don't go with the nucleus shape. I go with the granules. And then the other one is a monocyte and a lymphocyte. And the monocyte is big and large. It's the largest of them. And the lymphocyte is actually the smallest of them. And the nucleus is really large compared to the outside of the nucleus. These are the nuclei. So that's what we want to know about that. And then the oh, this is kind of cool. The chemokine, chemotaxis, and diapedesis is amoeboid motions. Is that the diapedesis means the white blood cells can squeeze through blood vessel walls in the capillaries, where we only have like an innermost layer of a wall. And the chemotaxis is a chemical attraction. So it's like taxi is like the taxi gets you somewhere, and chemo is the chemicals will guide the white blood cells to go somewhere. And so that's how I remember that. And amoeboid motion is just they have contractile elements, little subunits of actin, and they can move forward gently that way through tissue. So that's kind of cool. But that's not on the test. What's on the test is what those different ones do. And so the first one is the neutrophil. And that's the first eater at a site of injury. And so if we cut ourselves and we get some dirt coming into our skin, neutrophils will show up there. And as a matter of fact, what they do is they release destroying enzymes that are in their lysosomes, and sometimes they die themselves. And that's when you have pus. So when you see pus and you go like, ew, that's gross, you remember that the neutrophils died to save you. So if you ever feel depressed or so, you know you have superstars in your system, heroes that die for you. That's how important you are. So keep that in mind, just in case. The basophils are the next one. So that's the bluish ones here, the basophils. They release histamine and heparin, which are taking part in a hypersensitivity reaction. So that's your allergy stuff. And then eosinophils are part of limiting that excessive histamine, limiting allergic reactions, and they're also phyparasites. So that's what I want you to know about those. And then, oh look, these are actually, these three with the granules, they call them granulocytes as a group. And then the other two, the monocyte and the lymphocyte, they call agranulocytes. And so the lymphocytes, there are the B and the T cells. Those are your immune cells that work on a specific immunity. So that's an interesting topic at this point with the COVID, because we all kind of know about antibodies and antigens, how the spike protein and all that, that's the antigen of COVID, how that looks. And so we have white blood cells in our system, the B and the T cells, and they learn how an antigen looks, like how it feels, like the shape of it. And then they can learn how to make an antibody for that and neutralize that antigen, that pathogen. And so that's what they do. That's what the B cells do. The B cells, they make antibodies that then go very specific for one specific antigen. And the antigen is the marker that shows our system that, you know, there is a foreign thing in here and makes us sick. It's that marker that makes us sick, because what makes us feel sick is the reaction of the immune system. That's what makes us feel sick. If we don't have any reaction at all, it could be that something is attacking us and we're not having any ability to fight. And so that could potentially be the problem. So if you get a fever and we get a reaction, that's actually a good thing. It's just with COVID, that thing is just hecking too strong, and it damages other parts of the body. the lungs, and you know, we also know it does some function, some number to the heart, to the brain, depending on who is getting it. Anyway, that's the specific immunity. And the B cells make the antibodies, and the T cells, they attack those pathogens directly. They just shoot them down with, like, they call them perforins. There's like little bullets that are like little gun things, and they shoot them down directly. So they learn how to read the pathogen's antigen and then directly attack that thing. So that's what those do. So those are very, very powerful cells. We will learn how they are kind of kept in check a little bit, because they're kind of very powerful. We don't want them to kill the wrong thing, because that would be an autoimmune reaction, which we also know people have. And there's a lot of diseases that are autoimmune reactions. And then the last one of them, let me see. Yeah, on a test review, it said lymphocytes as B and T cells are part of the specific immunity attacking specifically targeted pathogens. And so that's what the point you need to know for the test. And then monocytes are also interesting because they're non-specific, so they eat stuff, but they recognize if something is foreign, and they then take that foreign, that marker, that antigen of the pathogen, and display it on the surface of their own cells. And then what they're called no longer monocytes, then sometimes we call them then we call them antigen presenting cells, or APCs. But the word antigen presenting helps you. So then those cells fire up what they call the molecular alarm and say, like, hello, we're affected. We got an infection over here. I'm holding it. Attack me. You know, let me show you what it is. Let me show you how it looks. These cells also have little spikes on them, the way they grow out. I think these look so freaking cool. I hope I could keep those pictures when I go through the whole copywriting process. But anyway, then they're also known as dendritic cells, because these spiky looking things in nerve cells are dendrites, and so they call them that as well. So these are just AKA, so you know, when you see that, you know that used to be a monocyte. And the cool thing about the monocytes is they go to the tissues and they live outside of the bloodstream in tissues, and then we call them macrophages. So if you see the term macrophages, you know they come from monocytes. And what's interesting, then they have different names. And so in the bone, for example, the osteoclast is a resident monocyte. I like the name in the lungs. In the lungs, they call them dust cells. And I feel like, oh, they're little dusters. They clean up the lungs. And so, you know, once in a while you get one of those. In the liver, they call them Kupfer cells because they look a little bit like copper, and so forth. We'll talk about the skin today. They're also in there. All right, so that's the different types of white blood cells that we worry about. Well, that they are, but those are the items we worry about for the test, is what I wanted to know about them. And then we get to the thrombocytes, and the thrombocytes are the platelets. They're very small little fragments that come from one big cell, and then they just, you know, they break up and are floating around in the bloodstream for a few days, and then they get extracted again. They are an important piece in blood coagulation or blood clotting. And it's actually blood clotting. The coagulation is one part of the process. But I want you to know those steps a little bit. And I wanted to know them. In the test, there's a question that will, you know, have you sequence them properly. And I want you to know the first thing we have is a vascular spasm that causes hemostasis. And hemostasis is when the bleeding slows down or stops. And vascular spasm means the blood vessels, the arteries have a little bit of muscle around them, and that muscle contracts, and then it squeezes the blood, makes it tighter, and makes the volume of blood that can go through it smaller. And so that way we stop the bleeding. So that's kind of helpful. And that process is done as called vasoconstriction. Vaso is a vessel, and constriction is constricting, is narrowing it down. And then we have that vessel wall damage here, and then the platelets start coming together and aggregate, slowly forming a plaque. But first they come together and they clot this, they break, they stop this damage, they stop this hole and patch it up as well as they can. And then that's where we have then the blood coagulation, and that's the step that we have fibrinogen go into fibrin. And see, there's a whole bunch of factors here that play a role in, and there's even more than that. It's like 10 to 12 steps. And I don't need you to study all of them. I just need you to know it's complicated. And the last step is the fibrinogen, which is a soluble fiber. So that's not precipitating out in solution, goes into fibrin, and that's an insoluble fiber, and that will clump together, which is what we want when we have the blood clotting happening. And so that's blood coagulation. And that's then when we don't just have platelets, we also bring red blood cells together and form a scab on this, and then the vessel can, so that will stop the blood from leaving, and then the vessel can heal. And so that's the platelet block formation. When the fibrinogen is made into fibrin and the RBCs and platelets are trapped, closing down that hole. Good. So that's good. And then we're gonna go from there to the lipoproteins, and those are shells of not phospholipid bilayer, but it's a simple layer. And on the outside, we have that hydrophilic part that can float in water. On the inside, we have these long tails, and those are hydrophobic, right? They are fatty. And so we can have fatty stuff be floating around in the bloodstream with these lipoproteins. And you know them, you know cholesterol stuff, you know they measure the LDL and the HDL. And what I want you to know about these is that the LDL carries the lipids from the liver to the body. And that's why we call it bad cholesterol, because it distributes the lipids. And the other one, the HDL, brings the lipids back from the liver to from the body to the liver. And that's why we call that the good cholesterol, because it's sort of a vacuum cleaner, cleans up the liver. I mean, it cleans up the lipids in the blood supply, the bloodstream. So that's kind of cool to know. And I just went to the doctor, and my lipids are a little bit high, although she said it was good. Except if I bring my HDL up a little bit, then the ratio is good, because it's about the ratio, a lot of it, not just about all your total cholesterol. It's about how much good ones do you have. And she told me, you know, if I do more exercise, and yeah, we're coming out of the winter hibernation, if I do more exercise, that should probably boost my HDL and should be fine. And so exercise helps with those things as well. It's not just diet. And you can think about that. What's interesting is when you contract muscle, you have myokines are secreted, and that's a hormone. And we actually should, well, we'll be in the endocrine system very soon. So the endocrine system, so that the muscle can also make a hormone. It's not just contracting and moving us around. It also secretes chemicals that go to the bloodstream and have then a reaction in the body. And so a lot of organs do that. It's not just the glands that we will talk about classically that do that. And so the muscle that contracts, that we use, will secrete the myokines, and myokines are known to do things like decrease blood pressure, increase the HDL. This is that one thing, and all that stuff that we consider, you know, these slow chronic diseases that are sort of taking us out are sort of decreased by myokines, by the exercise that the muscle contraction. And when we don't do that, we just laying around on the couch and study forever and ever, then we have a molecule that's secreted that is known as myostatins. Myo means muscle, and statins, I kind of think of static. And so that raises the, you know, LDL, decreases the HDL, and does all that kind of bad stuff, raises your blood pressure and all that kind of stuff. And so that's kind of interesting, but that's the difference in terms of what we need to know for the test of the LDL and the HDL is that the LDL carries the lipid from the liver to the body tissue, and the HDL brings it back to the liver. Any thoughts on that? Or are you cool?
I'm good.
All right, good. If anything shows up, interrupt me. Gives my mouth a little bit of a break from talking.
Okay.
But otherwise, we'll just keep going through it. But also make sure to interrupt me if things are like, I don't know if he's making any sense, because there's only 3 of you guys. And so I kind of rely on you to be sort of the canary in the coal mine for me and make sure I'm making sense. Okay, but as we go forward here, we have the oxygen transport, carbon dioxide transport. We want to know that the hemoglobin transports oxygen. You want to know that. Hemoglobin transports oxygen. The carbon dioxide is also transported in the red blood cell, but it's not attached to the hemoglobin. But that's okay. We don't need to know that. We just, I mean, we do want to know that, but for the test, it's about the hemoglobin and oxygen. And then we get to the blood groups. And the blood groups is the A, B, O, and then the plus negative. What are you, AB plus or negative or something? And so that's basically what blood groups are reactions that happen. No, when we used to transfer blood in the old days, and we didn't know about blood groups, all of a sudden some people could tolerate the blood from somebody else and others don't. And we had to figure out what's going on with that. And we learned that the blood itself, the red blood cells, has antigens on it, has markers on it that are not the same in everybody. And if we have markers that are the same that are carried in a red blood cell, and we transfer those blood cells with one another, then that's totally fine. But if we actually end up getting blood with cells with a different marker on top of them, we are in trouble. And the blood will clump together and create issues and strokes and all kind of bad stuff. And we don't want that. Hemolysis happens. And so we realized that we have 2 main marker type systems that are really making a difference. We have many markers that don't make a difference, but we have, look, about 100 different types, but so of these surface marky things, these antigens. And so an antigen, you just think of a marker. The antigen in our discussion in the COVID is often then synonymous with making us sick, because that's what the immune system reacts to. And is, then it's often interrelated with a pathogen or a virus. But the antigen is the part that is that marker. And so in us humans, we have the A and B antigen markers that are important. And then we have the RH marker that is important. And the one that we focus on for the testing stuff is the AB, because it's quite complicated. And so when you look at blood groups on the AB's always sort of 0 actually system, we look at what markers do they have. And so the group A has marker known as antigen A. The group B has a marker on the surface of the red blood cells. If you have group B blood, and that means you have the antigen B on your red blood cells. Then you have some people have both markers, A and B, and some people don't have a marker at all. And so those are O or 0, but they call it O, but that's how I remember it. And so what happens is if you have antigen A on your red blood cells and you are group A blood, you will have antibodies in your plasma present that are for the antigen B, the marker from the other blood group. And so that's where it gets confusing. So if you're group A, you have antibody B in you. So when you look at the blood group, you always remember that the description of the blood group is according to your antigens, not the antibodies, according to what antigens are on the surface of your red blood cells. So with group B, then they have antibodies for the A antigen. And so what you don't want to do is you don't want to mix and match those 2 bloods, because they'll clump out. If you give somebody who's group A, group B blood, that's like, oh, look at that. We have all these antibodies. We're going to react. And what happens when you have a reaction with antibodies, one of the things is they attach themselves to these markers, and they attach themselves to other red blood cells, and they clump out, they coagulate out, they precipitate out. And so that's not a good thing. And so we don't want to mix and match these bloods. So then the other thing that's cool, well, for these guys, it's really cool, because if you have both markers on it, you don't have no antibodies in your blood to those markers. So what that means is you can get anybody's blood and you're all just hunky-dory and cool because nobody's reacting to it. And so that's cool. So they call that the universal recipient. And then the ones who get messed up is the group O, because they don't have no markers, no antibodies. That means they have antibodies, no antigens. That means they have antibodies to both of the markers, A and B. And so that's a problem, because you can only get O group blood if you have that, but you can give it to everybody. So they all love you, but you're kind of stuck with getting just the one from your own people, from the, O people.
Wait, I get the group A and B, how it's universal recipient, but how does group O able to donate to the other groups?
Well, because, and it's known as the universal donor because of that, because it doesn't have any antigens to react to anything. So the blood cells, they don't have nothing to react to these antibodies.
So
the
antibodies won't attack it because there's no markers.
Yes.
Okay.
No antigens. Yes.
Okay.
And it is as physical as that. I mean, it's really about shape. It really is. And we see this with COVID because we really see that spike protein thing, right? And so that's the A-B groups, and that's what I needed to know about the A-B groups. The ABO blood contains antibodies to whichever antigen is missing. Group A has antibodies against B. Mixing corresponding antigens with antibody causes agglutination, which is the clumping out. And then group AB has no antibodies and is universal recipient. And group O is the universal donor because it has no antigens. So that's, if you break it down to what info gets put into a test question is that data point that, I need you to then be able to identify one of the different groups. And what we're not going to worry about in the test is the RH factor, because that's another thing if you're positive or negative. And that's because that has to do with sensitization. So you're having no antibodies, but once you're exposed to the RH and you're negative, then you create antibodies, and then you have a problem with it. And if you're negative, and then you have a problem with that, because what happens is if a baby and a mom are not the same, then that becomes a problem in the pregnancy. So we need to be concerned about that, but we can give the mom ROGAM at this point, and then that's not a problem. See these pictures?
Is it? I was gonna ask, is it all genetics for this, or is
this stuff is genetics? Yeah.
Okay.
Genetics, yeah. But isn't that cute? I thought the footsie was so cute. Anyway, look at that. We're moving right along. Well, we're also moving right along in time. Holy cow. You guys are really patient with me. Well, with that, we're going to go to the No, wait, we have to do the immune system. Yeah, we're going to go to the immune system. And look at the immune system. I only have one bullet there that I'm really worried about you knowing for the test, because this is mostly an anatomy class, but I want you guys to pick up some things of how things work. Otherwise, it's just a little bit bland just to look at structures only. But the immune system, so if things come into the body, the first things is the skin. Don't let things come into the body. And then when things are inside the body, we have a first line of defense is non-specific. Well, actually, no, here. Second line, the first line is don't let it in. The second line is non-specific. So you get a few things like, when you cut yourself, it gets red in the area and so forth. And then after that, is then, and sometimes then we recognize a problem with those cells that we call the antigen presenting cells, and then the third line gets activated, and that's the specific immunity. And that is the T cells, which are cells that are target specific pathogens, or humoral is referred to the antibodies that get secreted. But what I want you to know is the non-specific immunity is when we attack an invader non-selectively, and that's generally triggered with the inflammatory response. And the inflammatory response is, you visualize you caught yourself, well, don't do it. Or you know, step on some stupid Lego piece or something. The edge or you know, something that really breaks, doesn't just hurt. But what happens first is you get vasodilation. So the area gets flooded with blood to keep us, to isolate the bad stuff that can come in, and also bring a lot of immune cells to the area. And so vasodilation brings us heat, leaky, damaged capillaries, and that brings us swelling and pain or tenderness. And so those are the cardinal signs that we get, is heat, redness, tenderness, swelling, and pain. And that indicates that non-specific immunity is taking place in the body. And then the specific immunity, so then we have these macrophages that we just looked at in the blood chapter, that eat, you know, the bad stuff and then become these antigen presenting cells. And the other thing that they have on them, everybody has on the cell, is a matrohistocompatibility complex. Histology is cell cytology. So this is showing us if the cells are compatible with our body. So these are markers that indicate that we are self. We are our own self, our own body. And so the APCs, these antigen presenting cells, these macrophages, eat the bad stuff and then present that together with their own MHC, with their histocompatibility complex. And then that's the molecular alarm that they send to the white blood cells. The where is my molecular alarm picture? I don't know, probably took it out. So then that presents itself, this is actually better, that presents itself to one of the T cells, to that specific immunity, and that T cells, the helper T cells, recognizes the antigen and the MAC, and then it activates the specific immunity and says, hey, we gotta go attack this specific antigen. I just learned that we are invaded. You know, my friend APC told me about it. Let's go do the work. And so that's the helper T cells activates. Then further, you could see that here activates the T cells and the B cells to T cell attack the pathogen, the antigen's, you know, owner, so to speak, directly by killing it. And the B cells makes a lot of antibodies to then, and the antibodies, what they do is they clump together. They clump together the different pathogens, the different viruses. They neutralize them, so they cover the spikes. For example, in COVID, they cover the reactionary spikes so the system doesn't respond and doesn't have the fever and all that stuff. And then they clump out in solution, and that way we can get rid of them as a problem. And so that's what the antibodies do. And so that's the specific immunity, is the pathogens that are previously encountered sensitize the immune system, then it can be attack them selectively again. And that's what happens then when we prime the immune system, because the first time we're exposed to a new antigen, it's a slow learning process. Because the system has to learn what looks like and has to learn that antigen, and that takes time, because we just have a very few cells that are being able to recognize that specific antigen antigen. But once we are exposed one time, and that's, for example, the chickenpox. In the old days, you go to the neighbor if the neighbor's sick because you want to get the chickenpox in a time frame when you're young, and it's not a heart disease. It's just sort of like, you know, uncomfortable. It doesn't kill you. And so then after that, the immune system is primed, knows and understands what the chickenpox virus looks like and can attack it again. And what we can also do, though, we can do that process not naturally, we can do that process artificially, and we can immunize our system by presenting a non-illness making antigen that the immune system then reacts to. And that's what a vaccination basically is. We can also, and that's it's called active immunization because the system gets primed. The cells the cells are taught what to do, what antibody to produce. You also can have passive artificial transfer, and that's when you get a snake bite, that's the antivenom. So basically what you do there is you squirt antibodies that are already made specifically for one antigen into the recipient and flood their system with it, and so it acts for that time frame as long as those antibodies are present in the bloodstream. It acts like you have been immunized already, and so you have the benefit of these antibodies. And so we do that with COVID with an antibody transfer. They are doing that now. You know, that's what Trump got in the old days when it was, or whenever he got it, when it was just not available for people, the antibody transfer. And now the studies are out, and I think the Biden administration are trying to get these antibody, they has to be infused. So they get these infusion machines to old people homes and things like that, to when somebody gets COVID, you can then give them the antibodies directly there, because there's no time to wait for the 2 weeks until the immunization happens at that point. The vaccine happens at that point. So I think when you look at it from that perspective, the coolest part, you know, that I think we need to understand, you know, we can have a discussion about vaxxing and anti-vaxxing and all that stuff, but I don't need to get into that. What I do want to point out, though, is the process of what we do with the system, with the vaccines, that we actually sort of tickle our own system and say, hey, this is how it needs to work a little. Let you learn from that. I think that is really brilliant. It's not just like you have a knee that is old and you exchange it with a metal knee. You're actually working with the system, how the system functions internally. And I think that's probably, I would judge, that's one of the most advanced things that modern medicine has done for us, you know, and because it's not just deadening symptoms, it's really getting us, getting our immune system taught something. And so I think, you know, I want to keep it in mind, and then we can have the discussions one-on-one or so, and we can have different opinions of how to work with that. But I think we want to remember, what is it really about, and what is the function behind it? Because a lot of information that's out there, it's just like, oh yeah, it's gonna, you know, have you grow an extra ear, because, and then some of that stuff is just not necessary to be taught about. And the more you know the fundamental science, the more you can decide, does that make sense? Does that not make sense? And so forth. Because, you know, for example, if somebody is, you know, I have patients that don't want to get vaccinated, and I'm not going to argue with them about getting the COVID vaccine, because they might have good reasons for it, or they might have been having adverse reactions of vaccines before. And so there is definitely, you know, reasons to be understanding of people that don't necessarily do what we would be doing. Anyway, I
agree with you.
Yeah, if anybody has anything to say to this discussion, please go right ahead. You know, I think it's a very important topic right now.
No, I agree with you in that. If you want to get it, you can get it. And I'm not going to argue with you, because I see a lot of people on social media, they're like, oh, like, don't ever talk to me again if you're not getting the vaccine because you don't believe it, or like stupid stuff like that. Because it's like, if you want to get it, you get it, but you have your own reasons.
Yeah, you have to be, you know, I mean, you want to be sensitive. And I think, you know, a lot of, you know, like when it came to vaccinating my own kids, like with all those vaccines, and I think the medical community has done a bad job by not, but the doctors are not always that great in explaining things. And so there often is like, they don't meet anybody halfway. They're just like, oh, you don't want a vaccine, you don't understand. It's the best thing since sliced bread, and that doesn't help us not thinking what's wrong with this, because they're not telling us something. And when I worked with my kids, I waited where I could wait to give the vaccine. I waited until the kid is bigger and has more volume, and then the same amount of material going into the system can take better care of it. So that's how I dealt with some of the ambiguity of giving my kid like 50,000 million vaccines all in one swoop, and I'm not worried about that. That's my blood, my flesh and blood. So I think we want to be very gentle and with this COVID situation, have these, where we can have these talks, because for example, you can talk to a pediatrician if you have a kid and say like, could we spread these things out a little bit, or why do you put an MMR together all in once when it's such a high dose of vaccines, and a lot of the kids really suffer, even if it's just short term, but they might have a couple of nights when they're in distress, and we might not want that as parents. Because when I asked my pediatrician that question, a while back, when my 18-year-old was 1 year old, the pediatrician said, we give them all together because the parents don't bring the kids back. They're busy people and they don't want to go to the times. Like, oh, I'm fine, I can bring my kid multiple times. Let's just spread them out a little bit, so we don't squirt that many chemicals, regardless of good or bad, but that much foreign stuff into the small body all at once. And so, those are discussions I think we do want to have, and especially if you have people that that talk to you on social media, or so, that you really know that this just not it's not fundamentally how things work. For example, like my friend, he doesn't want to get the vaccine. He thinks it's a bogus thing or whatever thing. And he says, yeah, and then you have to get 3 or 4 vaccines a year because all these mutations. I think, but Ollie, when we don't have transmission, we don't have mutations. So you got to also look at that. It doesn't have to necessarily be that way. You want to look at all the data points you can find, and then, we can make our own decisions about it. Bene. Anyway, any other comments to that before I move on?
No.
Good. Then I better TMI, be quiet, don't talk endlessly about it. So let's go then to the endocrine system. And the endocrine system is a system that controls, and here it is, controls and coordinates functions of cells, body functions, by having glands secrete hormones in the bloodstream. They attach receptor on target cells and alter their functions. So that's what I want you to know there. It is composed of glands that secrete chemicals. I'm just reading the bullets from the test review, but that's on here. It is composed, the endocrine system is composed of glands that secrete chemicals, and chemicals are hormones, and hormones are chemical signals, and those are secreted into the bloodstream, and then they circulate throughout the whole body. And what's important there is the chemical then goes and specifically goes on to cells that have a receptor on it for that specific hormone. So not all hormones will work on all cells. It's up to the cell which receptor the cell has, and then the hormone, the chemical, will work on that cell. And then the receptor, so then the hormone is basically the trigger that the receptor will have some kind of a function going on to the inside of the cell, and then the internal machinery starts, or whatever needs to happen, whatever the trigger is for that. And so this system is actually going to be very closely related to the nervous system, which will come next, or after the skin. We'll go to the nervous system. And the endocrine regulates regulates the body by hormones going to the bloodstream and trickle through the bloodstream. The nervous system controls body function by sending a nerve impulse right to the target cell, and then there secrete a little hormone or little chemical, then it's called a neurotransmitter, and the receptor on the target will do the action. So from a perspective of chemical, receptor, and then reaction, the nervous system and the endocrine system work the same, or very, similar. There's small little changes, but very, very similar. And the difference is that the hormones are secreted into the bloodstream and travel slowly, so to speak, through the bloodstream, and the nerves fire an impulse, an electrical impulse down the nerve, and then right at the target secrete the hormone or the chemical. You can sort of feel that if you drive. I don't know if you guys drive, but if you drive, or if you've been a passenger in a car, it's even scarier because you have a near accident and you swerve out of the way, and that's the nervous system functioning. That's a really fast reaction. But then you slowly get the jitters in your system and you get nervous. It's like too much coffee. And that you can feel that's the hormones working on your system. So you see that, and those last much longer than the swerving out. So you see the difference between speed and longevity in that example, kind of. So but the two differences that we need to know is it fast, is it slow, are the effects long lasting, or are they short? So the endocrine system is slow and long lasting. Then we get to the different glands, and before we do that, I want to talk about the hypothalamus briefly. So the hypothalamus is located right here in the brain, and that is sort of the master gland that is right in here. So that's the brain, and then that's the master gland. And then from there, a little bit below that, in the sella turcica, that's why we studied the sella turcica, is the pituitary gland. And in the old language, they call that the hypophysis. But anyway, that's just, some of the words are still a little bit in there. So I want you to know that that's what it used to be called. So anyway, the pituitary gland sits in the sella turcica and reacts to the hypothalamus, but then itself secretes a whole bunch of hormones into the system. And so what happens is the hypothalamus sends, and you can see that the hypothalamus sent, oh no, that's the wrong one. Hold on. Where is it? I don't think I have a picture of that. But there is a little blood supply going here. So the hypothalamus sends little hormones into the bloodstream here, hypophyseal network. And that stimulates the pituitary gland to secrete these hormones or not secrete these hormones. And so the hypothalamus has, for example, growth hormone. This GH is growth hormone releasing hormone or a growth hormone inhibiting hormone. And depending on which one it secretes and tells the pituitary gland, or that then tells the pituitary gland to secrete more growth hormone or to inhibit the secretion of growth hormone. So that's why the hypothalamus is the master gland. So it's the boss that tells the worker, which is the pituitary, what to do. So that's the front part of the pituitary gland, how that works. And it secretes all of these hormones: adrenocorticotropic hormone, thyroid stimulating, growth hormone, prolactin, blah, 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 all these things. And we learn a little bit of what some of them do. But you don't need to list them. But then we have a different part of the hypothalamus, the pituitary gland, and that's the posterior part. They also call that the neurohypophysis. The front part, they also call the adenohypophysis. Adeno, whenever you see the word adeno, you think gland. Neuro, you think neurology, you think nerve, you think brain, you think that kind of stuff. And what that part of the pituitary gland is, that is actually the end point of nerves that travel from the hypothalamus down to that portion. And then from there, we secrete chemicals made by the hypothalamus directly into the bloodstream. And so the neurohypophysis works a little bit different than the adenohypophysis. So it's the chemicals for the posterior part are secreted or made in the hypothalamus and then released in the posterior pituitary gland. And those hormones are antidiuretic hormone and oxytocin. And I want you to, no, that's pretty much it. You don't need to, for the test, know those two hormones. That's more for the quiz. The other thing that the hormones that are from the hypothalamus that are the releasing or inhibiting hormones, they also call them liberins as the releasing hormones or statins as the inhibiting hormones. That's just on that review. I'm not so sure why I put that there, and I can't find it in the text right now. But here are these other hormones, how they function, and then what we could do is we can go to the next place, because the next dot there already talks now about a different gland. So it goes now through the different glands. So the first one was the pituitary, but I don't need you to list all the hormones. It's just a lot of hormones. But it's interesting. Absolutely. It's just a lot of memorization. The pineal gland, I want you to associate that with melatonin. And melatonin, I want you to associate with sleep, aiding sleep. It's also an antioxidant, but it helps with the night-day cycle. Then the next gland we're having is the thyroid gland, and that has to do with the rate of metabolism. So that has to do with how fast you make an ATP. And then also on that thyroid gland, we have, when you look deeper on it, on a slide, you have these thyroid cells, follicular cells, and then the thyroid follicles. And follicle is kind of like a pool of liquid, which is this hormone thyroxine in here. And then you also have these other cells, they're blue in here, and those are known as the parafollicular cells. And the parafollicular cells secrete another hormone, and they secrete calcitonin. And calcitonin is a hormone that decreases blood calcium level. This is blood calcium levels, and the calcitonin decreases that. It brings it down, levels fall. So I remember that by calcitonin tones my blood calcium down. So that's calcitonin tones it down. That's how I remember it. And then when we turn this gland here, this thyroid gland around, we see the back. And the back are the little small bean-looking things. They're the parathyroid glands. And the parathyroid glands secrete parathyroid hormone, or PTH, and the parathyroid hormone raises the blood calcium level. So if the blood calcium level is low, it does all these things. It increases the release from the bones. It takes more from the intestine, doesn't absorb or reabsorbs more from the urine, and then that raises the calcium level back up in the blood. So we want to have calcium a very specific level in the blood, and so that's why that is important. The same we do that with is the sugar, the pancreas. That's also one. But first, before we do that, we go to the adrenal gland, and the adrenal gland has two parts. It has a cortex. See, it sits on top of the kidneys. Renal means kidney. Adrenal is on top of it. You're adding it on. So it has this cortex, and the cortex has a couple of different layers to it. And every layer secretes a different hormone. And then on the inside, we have a medulla, and that also secretes a hormone. The medulla, as a matter of fact, secretes the hormone that makes you jittery after the almost car accident. That's the adrenal medulla. That's where we get epinephrine from. Adrenaline is that. That's the same thing. The adrenal cortex secretes multiples. The top layer of the cortex secretes aldosterone. And aldosterone, what I want you to remember aldosterone doing, it reabsorbs sodium in the kidneys. And whenever you have sodium be reabsorbed in the kidneys, you will have water be also reabsorbed in the kidneys. So that will help bring water, bring liquid back into the bloodstream. So that's aldosterone. And then we're going to have the cortisol. And the cortisol is a long-term stress hormone. So if we're under long-term stress, it will make sure we have energy, available, but it will do that to the cost of other systems. So the immune system goes down a little bit, for example. So that's cortisol. So that's also decreases inflammation. That's why we use cortisone as an injection if we have joint inflammation. And then the last one there that we want to talk about is we have androgens, and we have a sort of testosterone in that zone that gets secreted there. And that's an androgen, and build up masculinization hormone that's secreted by both women, female and male bodies. And so the women, the female, have a little bit of testosterone creations here too, which is important for our normal functioning. And so that's what's secreted in those different zones. And we already talked about the adrenal medulla, and then the other one that I'm interested in talking about is the pancreas here. And the pancreas is an interesting gland because it does a lot of intestinal enzyme production, and then it squirts those into the first part of the small intestine. We'll talk about that in the digestive system. But it also secretes insulin and glucagon. And insulin is a hormone that brings the blood glucose away from the blood. And so if you eat a very sugary meal, then afterwards the blood glucose level goes up and spikes. Insulin gets secreted by the pancreas, and that brings the blood glucose level down and brings all the glucose into the different cells. And so that's one of the hormones. The other one that it secretes is glucagon, and glucagon does the opposite. It can break down glycogen storage. It can break down stored glucose molecules if the blood sugar goes too low, and raise the blood sugar level up that way. So that's kind of cool. And then we got the sex hormones, and they secrete, the gonads, and they secrete sex hormones. Cool. Look at that. I got 2 minutes left. Let me go through that. Here, the skin. God, these are long sessions. When you look at the skin, the integumentary system, we have the top layer, that's an epidermis. Then we have a lower layer, that's the dermis. And then you have a subcutaneous layer that's below, or subcutaneous fat layer, sometimes it's also called. The dermis, the epidermis comes with all these different layers. Basically, you make little squamous epithelial cells. Well, they're more cuboid here. And then as we get more and more to the surface of the skin, those cells accumulate keratin, which is a dehydrating a molecule that makes the cell hard and water resistant. And the cells slowly die off, and then on top, the top layer is just flaky dead cells, and if we bang into something, they just fall off, and so we don't have a problem. We just create it back from underneath, and get more layers to it. You don't need to study all the layers for the test, but the underneath layer is the the dermis, and the dermis gives the skin. This is here. It gives the skin resistance to tearing and makes it plastic, the ability to deform. It contains a thick network of collagen and elastic fibers. And so I want you to know about that on this slide. And then after that, we go right into function. The skin function is a protection. So yeah, if you bang into something, you don't bleed. You just have skin that falls off a little bit, but that protects your body. Also protection because it's an immune system. There's also protection, the first line of defense. Don't let stuff come in. Very, very important. And then the other thing is we have a temperature control. That's back to the blood vessels too. You bring the blood vessels closer to the skin, and you make them wider there, and the heat radiates off. Or the other way around, you bring the blood, if it's too cold, you bring it to the essential organs and make sure those have enough heat. Or also the other thing we do in the skin, we sweat. We have sweat glands, and again, liquid carries a lot of heat with it, and it can get that heat radiated off via sweat, evaporated, and carried from the inside of the body to the outside, and so that's kind of cool. Water balance. Epidermis prevents water loss. I often visualize like we come from the ocean, so we're like a bag leather skin and liquids on the inside. And so the skin makes sure the liquid stays on the inside. And remember, we are so much water. And so we want to make sure that stays on the inside. Then the skin provides sensory function. We can have pain, we have temperature senses, we have touch in there, we have hair. You should have seen when I first cut my hair off and I didn't have hair to alert me when I would bang into something. I bang into a whole bunch of stuff. I must have lost a lot of brain cells at the first. Now I'm used to it. I mean, it doesn't hurt no more when I bang. But so the hair actually, then you realize how hair is actually a tactile sensation thing and helps us feel the outside world from that perspective. Also communication, we can blush, that's a communication. So that's also, or turn pale, depending, like in fear or blush when we're embarrassed or so. That's a level of, that's a communication thing. And then the last tab there I needed to know is the skin appendages are hair, glands. We have sweat glands and we have sebaceous glands. Sebaceous glands go into, here it is, into a hair shaft all over the body, and they secrete an oily substance. And then the last, and so that's kind of like the natural, lotion. When I don't put on lotion, I always tell myself that. We got sebaceous glands, go to work, people. And then the nail, of course, we have a nail that is also an appendage to the skin. And the nail's kind of cool because with the bone in here and then this hard thing here, when we squeeze something, it has this backstop. And so we can actually pinch something. If this would be just skin and skin, it would be really hard to pick up small little things. So it's a practical piece. Of course, they're also very pretty, depending on how we make them. All right, so that's all I have. Look at that. We lost somebody. How are you guys doing with that? All that information.
Good.
Good. Any questions, or that's pretty clear, just a lot?
Yeah, it was pretty clear.
Okay. So then good. Then let's just call it a night or a day. And next week we'll pick up where we get with the nervous system. If you have any questions that come up, just shoot me a text. We can make sure we solve them on the outside or bring them to the class. And I think that's about it I have. Any last thoughts on your end?
Not for me.
Okay.
No, I was just thinking when we were talking about the immunization, I felt like I could talk about that forever, but I didn't want to continue it on.
No, that's okay. I know, and we do a lot of stuff, so it's a little harder to get these discussions flowing a little bit, but I'm kind of glad we're covering it because it is kind of interesting how the world works right now, and what's going on with all of that. Anywho, with that, let's call it a day.
All right. Have a great week. I'll see you next week.
Same as you guys. Thank you so much for paying attention. Have a good one. Bye.
Bye.
Bye.